To do this, let us start with the circuit of the boost converter. Okay. What we will do, or what we will try to do, is to have an understanding of this higher order converter in a more intuitive way rather than a mathematical way to begin with. Okay. So we start with the boost converter circuit, which has an inductor, a switch, and then you have a diode and the output capacitor, which would try to maintain this output voltage constant. Right? Whatever load you have would then be connected across this output voltage VO. Okay. So this is your L and that is VG. Okay. Now we know that for this circuit, assuming continuous conduction mode, VO by VG is equal to 1 by 1 minus D. Okay. This is the relation for the output voltage as long as your inductor has a continuous current flowing through it. Okay. Or you could say that the output voltage VO is equal to VG divided by 1 minus D. Okay. Now what we do is we will try to redraw this circuit in a slightly different manner. Right. At the output you can see that we have a series combination of a diode and a capacitor. Okay. So if I simply redraw this circuit by interchanging the positions of this diode and capacitor, it should be obvious that this is not going to change anything as far as the operation of the circuit is concerned. Okay. What we have done is we have taken the capacitor that was placed here and put it here, and the diode we have put it over here. Right. This does not change anything as far as the operation of the converter is concerned. So you will end up with a voltage. Let us now call this voltage as VC1. This capacitor, we call it as C1, and this voltage across the capacitor VC1. Right. So what then would be the value of VC1? Again, VC1 would simply be equal to VG divided by 1 minus D. Okay. Now if that is the case, let us try to look at what would be the voltage across this diode. Okay. Let us call this as D. What would be the voltage across this diode D? Well, you have two situations. One, when the switch is on. When the switch is on, you will not have the diode conducting, and therefore when the switch is on, the output voltage would be, this terminal would connect to the negative portion of the capacitor, and this terminal would get grounded through this switch when it is turned on, so that the diode voltage becomes equal to minus VC1. Okay. This is when, let's call this switch as S. This is when S is on. Okay. And when S is off, what should be that voltage? When S is off, the diode is conducting, and therefore the voltage across the diode is going to be 0 when S is off. Okay. And this interval lasts for a duration of D times Ts, where D is the duty ratio, and this happens for 1 minus D times Ts. Okay. So if you were to now look at again this circuit and then plot the diode voltage, right, what we'll do is first plot the switching signal for the switch. Let's say that is like this. Right. This is your D times Ts, and that is 1 minus D times Ts. Therefore, as we said, the diode voltage when you have this dTs interval, that would be equal to minus of Vc1, and then for the remaining portion it would be 0. Okay, so this value is negative Vc1. Okay, now what we will do is, if you look at this diode voltage, you find that it has a negative average value. Right? It has a pulsating voltage waveform across the diode with a negative average value. Okay? And so what we can try to do is filter out this diode voltage using an LC filter, similar to what we have done for the buck converter. We put an LC filter now here. Right? We can call this as L1 and this as L2 and this as C2. Okay? If you do that, what you are going to get here, let us call that voltage as V0. And this V0, as we know, because LC filter is a low pass filter, you will get whatever DC component is there in this waveform of diode voltage. Okay, and that is easy to calculate. The average value of the output voltage is therefore equal to the average value of Vd, and Vd average value is therefore 1 by Ts and minus Vc1 times dTs plus 0 times 1 minus dTs, that doesn't contribute anything. Therefore this becomes d times minus d times Vc1. Right? Now we already know what is Vc1. Vc1 is Vg by 1 minus d. Right? Therefore we can say that V0 is equal to minus d times Vg by 1 minus d, or V0 by Vg is therefore going to be equal to minus d divided by 1 minus d. Okay, so what we see that the particular converter that we have now obtained has the same voltage transfer function as that of a buck boost converter, but now you have one inductor at the input which would ensure that you have a continuous source current, and one inductor at the output which would ensure that you have continuous energy transfer at the output. Right? And the output voltage is again can be stepped up or stepped down, but minus d by 1 minus d indicates that the actual polarity of the output voltage that you get would have plus here and minus here. Right? And therefore this circuit that we have obtained just now from the boost converter goes under the name Cuk converter. Okay, it was first proposed by Professor Cuk, and therefore is given his name. It's written in this manner as Cuk converter.